Hello and welcome. In this lesson, we'll go over the step-by-step process solving various types of logarithmic equations. I've organized the examples into two groups, solving log equations by using the laws of logarithms and solving by using the properties of logarithms. However, there is no clear cut between the two types of equations or the two methods because most of the time we have to use them in combination. Let's take a look at our first example. Log with base 3 of 9 plus log with base 3 of x equals log with base 3 of 24. As you can see here, we have only log terms throughout the equation, and all the log terms have the same base, 3. Our variable, the one we are solving for, is x, and it appears in one term only. So what I would do in this case is keep log with base 3 of x to one side of the equation and bring the constants to the other. Notice how here we have the difference between two log terms, which means we can use the quotient law to simplify the two terms or to subtract them. So log with base 3 of x equals log with base 3 of 24 divided by 9. As you see here, we have two log numbers that are equal to each other, and their bases are the same, which tells us that the numbers inside log, or the terms inside log, must be equal. So x equals 24 over 9, or in a more simplified form, 8 over 3. And this is the answer. This is not the only way we can solve this equation. We could combine the terms in various ways. And normally I would combine the terms that have the same base. For example, we could also leave log with base 3 of 9 in the same side as log with base 3 of x. So I'm going to write the other method on the side. And that will make log with base 3 of 9x, that's product law, equals log with base 3 of 24. So the whole idea behind it is to be able to minimize number of terms, okay, and be able to combine the logs with the same base. 9x equals 24, and we'll arrive to the same solution, which is x equals 24 over 9, or x equals 8 over 3. Moving on to the next example, we have log with base 7 of x squared equals log with base 7 of 16. So we have one log term in the left and one on the right side of the equation, and both have the same basis, which tells us that x squared must equal 16. Square root both sides, and we'll say that x equals either plus or minus root of 16, or x equals plus minus 4. Normally, we wouldn't like to have a negative number inside the log, but in this case, because x is squared, x is allowed to be negative. It will again produce a positive number. Next example, we have the example of log 2x minus log 148 equals 2. So in this case, we don't see the base, but we know that when we don't see it, the base is 10. Now, I am thinking of keeping the log 2x in the left side of the equation. If I brought the constant term to the other side, then it would be a little bit difficult to combine the two terms because one is in log form and the other isn't. So what I would do in this case is combine the two terms in the left side of the equation, since they already have a common base, and we'll say that the left side can turn into log with base 10 of 2x divided by 148. Division because we have subtraction here. And that would equal, 2. And I wanted to make the base visible because now we are about to use it. So remember that we need to solve for x. We'll simplify the expression inside the log. That's x over 74 equals 2. To solve for x, which is inside the log, now we are going to convert this log statement into an exponential statement, which means that I'm going to take the base of 10, bring it to the power of 2. 2 is the log or the exponent, equals x over 74. So 10 to the power 2 is 100, which will make x equal to 7,400. 7,400. And voila, this is the answer. Now, I've prepared a couple of examples for you to try, to practice, so you may pause the video and try on your own. I will quickly solve them in the meantime. So again, I have 30x, 5, and 12. All the terms are log terms, very similar to the first example. So I have the choice of either combining the terms on the left side or taking the numbers to the other. I would take the numbers to the other side in this case only because I like the product law better than the quotient, but the same thing, same idea. So we have log with base 2 of 30x equals log with base 2 of 12 times 5. 12 times 5 is, keep forgetting the x there, is 60, which tells us that 30x must equal 60. Remember, the bases are the same. The log numbers have the same value. So 30x must be 60, which will make x equal to 2. Next, log of x minus log x squared equals 12. So what I would do in this case is combine the two terms, and we'll say that log of x over x squared, remember, we have division or quotient law, equals 12. So in other words, we'll say log of 1 over x equals 12. Now we're going to use the exponent properties or log properties, you can say. So we have 1 over x. So we'll convert the log statement into an exponential statement. Equals the base 10 to the power of 12. So that will make x equal to 1 over 10 to the power of 12, or 10 to the power of negative 12. Voila. Next, we have log with base 2 of x plus 3 plus log with base 2 of x minus 3 equals 4. So I would combine the two terms in here by the product law. We have log with base 2 of x plus 3 times x minus 3 equals 4. Remember, because of plus, we multiply. In other words, log with base 2 of x squared minus 9 equals 4. We have to be careful and keep this in brackets because we don't want to assume that, look at this, without brackets, we don't want to assume that only x squared is inside log and we're subtracting 9, right? So we're going to say that x squared minus 9, which is expression inside log, would be base of 2 to the power of 4. So x squared equals 9 plus 2 to the power 4 is 16. Oh, that's a nice number. So that's 25, which will make x equal to plus or minus 5, the square root. Now we have to be a bit careful here because some of the values may be unacceptable. So if x equals 5, we'll say that the log with base 2 of 5 plus 3 will be log with base 2 of 8. This number exists. But And the other term, which is log with base 2 of x minus 5, would be x minus 3 would be 5 minus 3. So that's log with base 2 of 2. That exists as well. If x equals negative 5, though, we'll end up with log with base 2 of negative 5 plus 3, which is log with base 2 of negative 2. This doesn't exist. And this is enough for us to reject the root or the solution x equals negative 5. So therefore, we'll say that the only solution we can accept here is x equals 5. And voila. Now let's move on to the next group of equations. We have solving log equations by using the properties of logarithms. So here we have 3 to the power x equals 21. You probably tried to solve one of those equations in grade 11. Probably used trial and error. We're going to use logs now, and we're going to solve these equations with high precision. Impressive, isn't it? So here we go. If we have 3 to the power x equals 21, the variable is in the exponent. We cannot access this exponent right away, and this doesn't even look like a log equation. But as a matter of fact, we need to use log properties in order to solve for x. So we are thinking, how can we access x? One of the ways to access x here would be by converting this exponential statement into a logarithmic statement. And we'll say that x equals the exponent or the log. We must raise the base 3 to obtain 21. And this would be the exact answer, as a matter of fact, and you can stop here. If we want to find the approximate answer, then we can write this as log of 21 divided by log of 3. Because we can use a change of base formula here, right? And I chose the base 10 because that's what the calculator provides. And log of 20, what was this? 21 over 3 would be, sorry here, oops, advertisement. So log of, oops, here we go, too many oopses. So log of 21, I think this calculator works the reverse way, which means I have to press 21 and then log it, and then divide this by, I'll open brackets here, I want to be safe, 3, and then log that, and that would equal 2.77. That's a nice number. So we'll say that x equals 2.77 would be the approximate answer. Now, the equations with log properties are different actually in terms of variety of solutions or paths that you can follow in solving them. So various forms of the equations or various arrangements of terms in an equation may require different strategies to solve them. So we're going to try to go over as many examples as possible. So here we are again. We have 5 to the power 2x plus 1 equals 6 to the power x minus 2. So in the previous example, we were able to actually solve the equation for x by simply converting the equation from exponential to logarithmic. But this time, that can be a little difficult. So what we do in this case, and it's a very common method of solving equations, is we're going to take the log of both sides. And I would take the log with base 10 of both sides. So now we have log of 5 to the power of 2x plus 1 equals log of 6 to the power of x minus 2. Okay. Now notice that here we have a power 2x plus 1. We can use the power law to take 2x plus 1 out because we want to access the variable, right? So we have 2x plus 1 log 10, right? Sorry, log 5. Sorry, but equals x minus 2 log 6. Now be very careful. X minus 2 must stay in brackets because it's a binomial form. And now we can expand, multiply by log 5, every term in the left side, by log 6, every term in the right side. And then we have 2x log 5 plus 1 times log 5 equals x log 6 minus 2 log 6. And I will be very careful to write the variables and the coefficients first and then the log after, because if we were to bring log to the front, say for example, if we wrote log first and then the 2x, it will be very easy to mix up the numbers and not be able to identify where the x is going. Is it inside the log or is it outside it? So now that we have easier access to the variable x, here is x in the left side and we have x on the other side, we'll bring the terms that carry x to one side. The left side is my favorite, and I would also rewrite them slightly differently. So here is x and then 2 log 5 and then minus x log 6 equals, we already have negative 2 log 6 on the right side, and then we are bringing log 5 to the right as well. That will become negative minus log 5. Now, as you can see here, x is the variable we're solving for, and is going with this funny looking coefficient. So in order to isolate x, we will factor x out from each term. So we have 2 log 5 minus log 6 equals, and what we see in here is a negative sign, which we can take out, and then we'll have 2 log 6 plus log 5. To isolate x, we are dividing both sides by 2 log 5 minus log 6. And you probably see that we can hopefully combine these two. So we can bring the coefficient 2 inside the log. And down in the denominator, we'll have log of 5 squared minus log 6. Obviously, you can do them faster, like the simplifying, but I'm trying to go as slow as possible so I won't lose anyone in the process. So we have these two terms simplified, and the right side is log of 6 squared plus log 5 over log of 5 squared, which is log 25, minus log 6. We'll continue simplifying a bit more. So we have negative fraction log 36 times 5 and log 25 divided by 6. So we'll say that x equals (36 times 5), that's 180, so log of 180, divided by log of 25 over 6, and we'll leave it in this form for now. So the bases are both 10, so we can write it as log of 25 over 6 of 180, so keep this as a base as well. But since we have a fraction for denominator, then we'll leave it in this form. Let's move on to the next example. In the next example, we have x to the power of log with base 2 of x equals 16. So we see x appearing in the base of this exponential number and inside the log as well. So what we're gonna do is we're going to write this exponential statement into a log statement. We'll say that the exponent log with base 2 of x is, so this is the exponent we say, or the power or the log, with base x of 16. So we have kind of a mixture of terms in here. So what we're going to do is, you see that we have x appearing in both of them. I'm going to do a change of base formula. And I wanted to think about it. What would be a good common base to use in this case? So I'll rewrite this as log of x over log of 2, one thing at a time, equals log 16 over log of x. So a good base to use in this case will be a base of 2. And that's because 16 and 2 can be written as exponentials with base 2. So now we have log with base 2 of x over log with base 2 of 2 is 1. That's the logarithmic properties, equals log with base 2 of 16 is 2 to the power 4 over log with base 2 of x. So log with base 2 of x equals, the numerator is 4 because log properties, log with base 2 of x. So we have a rational function here. Log with base 2x is our unknown and was solved by cross multiplying. So log with base 2 of x times log with base 2 of x. I'm going to take my time here so that I won't lose anyone in the process. It's very easy to confuse this with some power law, product law. Be very careful. We are multiplying log with base 2 of x by itself, which means that we practically here we have log with base 2 of x squared equals 4. Which means that to solve for log with base 2 of x, we need to take the root of 4, so plus or minus 2. So you square root both sides. And we're going to derive two solutions, or consider two solutions here. Either log with base 2 of x equals positive 2, or log with base 2 of x equals negative 2. To solve for each equation, we will have to use the log properties again. So we'll say x would equal 2 to the power of 2. So this is the base 2 to the power of 2. Or x would equal 2, the base 2, to the power of negative 2, which is 1 over 2 squared, or 1 over 4. So we obtain two solutions here. One is x equals 2 squared, or 4, and one is x equals 2 to the negative 2, or 1 over 4. Quite an example this was, wasn't it? Let's take a look at our last example. We have x to the power of root log x equals 10 to the power of 8. Okay, so let me zoom in. So again, we have x appearing in two different spots, in the base of this exponential number and inside the log. So what we are going to do is access this power first. We'll say that the square root of log of x is the exponent, this is an exponent, remember, or the log, we must raise the base x to obtain 10 to the 8. So we'll write this down, the log with base x of 10 to the power of 8. So we'll write this in a simpler form. So we'll say log of x, the whole thing is to the power of 1 over 2. Remember, this is not a coefficient, it's not one of those powers that you can bring in. Equals this power of 8 here can easily come to the front. So that will change it to make it log with base x of number 10. Now we're going to use the change of base formula to write log with base x of 10 into log of 10 over log of x. And guess what base I'm using? The same base that we see here, which is the invisible base or the base 10. So as you can see here, this 10 will sit inside log and the x will be in the log, in the denominator. So we'll simplify it just a bit more. So we have log with base 10 of x to the power of 1 over 2 equals 8. Remember that log with base 10 of 10 is 1. Ask the calculator if you don't believe me. And here we go. We have log with base x to the power of 1 over 2 divided by 1 equals 8 times 1 over log x. And we can also write this 8 times 1 over log x as 8 over log x. So here we go, we have log of x to the power of 1 here, log of x to the power of 1 over 2 here, cross multiply, and we'll get log of x to the power of 1 over 2 times log of x to the power of 1 equals 8 times 1. So log with base 10 of x to the power, here we have 1 over 2 plus 1, which is basically 3 over 2. And I'll write this down because I know you know how to add these two fractions. Equals 8. So again, our goal is to isolate x. So we'll start with the power. We'll bring both sides of the equation to the power of 2/3. So that will allow us to have easier access to x. And number 8 is 2 to the power of 3 to the power of 2 over 3. Notice how nicely they simplify here. So we have log of x equals 2 squared, or log of x equals 4. And now we know what to do. We have a base of 10 hiding in here. So x equals 10 to the power of 4. So finally, we discover that x equals a 1 with 4 0 or 10,000. And this is the end of the lesson on logarithmic equations. Obviously, you can see that there is a combination of exponential and logarithmic equations by solving them. And there is definitely a connection between log and exponent. Don't you think so? So thank you very much for listening to my lessons. And thank you very much for choosing to learn from me. Leave me a comment, ask me any question, and I will try to answer as soon as I can.